Hi, everybody. This is Dr. Anna, and today we're going to talk about the plate tectonics, which is one of the most exciting topics, as you will see.
Plate tectonic theory was not accepted for centuries because no one could adequately answer the question, what is the mechanism that drives the plates? Antonio Snyder Pellegrini, who proposed that the shape of the continents, supported by fossil evidence, argued for the origin of a single continent, which not only joined the continents across the Atlantic Ocean, but also included Australia. No one, however, could explain how the continents moved. Bathymetric surveys in the following decades unveiled an extensive submarine mountain ridge between the continents that ran the length of the Atlantic Ocean. Meanwhile, seismic data began to reveal Earth's layers, a core, a crust mantle boundary, and a thick outer layer called the lithosphere that lay above a less dense asthenosphere. In 1912, German meteorologist Alfred Wegener, also intrigued by the fit of the edges of the continents, championed the concept of continental drift, based on his study of similar rock types, geological structures, and fossils on both sides of the Atlantic. To make it work, he hypothesized that the mechanisms causing the drift might be the centrifugal force of the Earth's rotation or the change in its axis of rotation. Wegener also speculated that, quote, the mid-Atlantic ridge is continuously tearing open and making space for fresh, relatively fluid and hot material from depth, end quote. His views were considered preposterous and improbable, and were rejected by most Earth scientists. Following the discovery of radioactivity in 1896, it became clear that Earth's interior was heated by radioactive decay, and that the insides would be largely molten. Indeed, by 1926, a liquid core was determined. In 1927, geologist Arthur Holmes, studying radioactive decay, proclaimed that mantle convection was the answer to Wegener's missing power source to drive continental drift. He based it on the fact that as a substance is heated, its density decreases, and it rises to the surface until it cools, when it sinks again. But convection of the solid mantle alone was still unpalatable to most geoscientists. Nuclear bomb testing in the 1950s motivated the establishment of the worldwide standardized seismograph network to monitor explosions, prompting a greater concentration of seismograph stations. The increased data allowed seismologists to precisely locate far more earthquakes, revealing that most occur in discrete areas, near trenches and along mid-ocean ridges. Decades after Wegener's death, geologist Marie Tharp, left in the lab to examine data from ocean floor field surveys, theorized that mid-ocean ridges appeared to be extensional rift valleys formed by plate motion, thus paving the way for the acceptance of Wegener's continental drift theory. Her colleague, Bruce Heezen, initially skeptical, published her work in 1956 under his name, but ascribed the extension to an expanding Earth theory. It wouldn't be until the mid-60s that he would accept Tharp's interpretation of plate motion. Curiously, it was Harry Hess who, in 1962, was credited for recognizing that oceans did grow from spreading ridges. He also defined ocean trenches as locations where ocean floor was destroyed and recycled, but he too lacked geophysical evidence to confirm this theory. Just 1 year later, this concept was supported by ocean floor magnetic surveys that revealed symmetrical patterns of magnetic striping on either side of the mid-ocean ridges. These stripes were found to be the same age at similar distances away from the ridge on each side. While pondering the mystery of how volcanoes, such as the Hawaiian island chain, could be so far from spreading ridges or subduction zones, Tuzo Wilson proposed the plates moved over hotspots. Following this breakthrough, with the discovery that ocean ridges were connected with transform faults. The science rapidly blossomed with the definition of the three main plate boundary types: divergent margins, where plates move apart; convergent margins, where plates push together at subduction zones or mountain ranges; and transform margins, where plates move horizontally past each other. As geophysical evidence supporting plate tectonics accumulated during the 1960s, scientists revived Holmes' theory of mantle convection as a driving force for moving the plates. Mantle convection assuredly plays a role, but it doesn't explain how some plates creep along faster than the convection currents beneath them. This led scientists to a fundamental force: gravity. Gravity acts on the tectonic plates, resulting in what are now referred to as ridge push at the spreading ridges and slab pull beneath subduction zones.
If you remember from physical geology, we learned about the structure. As you remember, we have three main plate tectonic environments. One is the extensional. This is the figure which representing that. The other one is the compressional, which is represented by this figure here. And the last one is the transform plate boundary and represented by that slide. Let's talk first about the extensional setting. We'll find along divergent plate boundaries, divergent. If you have a divergent plate boundary and the plates are extending, that means that the forces are acting away from each other. The most common type of fault, which happens when earthquakes pop up, will be the so-called normal fault. This black diagram is representing normal fault. This here is the fault plane right here. That's like the side view of it is the fault line. And the fault plane and line divides the block which we are showing here into footwall block and the hanging wall block. Now, if we pick a layer and we look at this brown layer, you can see that the same brown layer on the hanging wall block went down. So that's what we call normal fault. And the fact that there is extension here can be well seen by following the layers and see what they do relative to each other. So when we look at this brown layer on this side and then on down here, and if we look at the front part of this block diagram, you can clearly see that this brown layer is missing right in this area. This is what we call the relative lengthening. So that is the distance relative lengthening. I just wrote it like that, relative lengthening. How much extension happened along this divergent plate boundary at this earthquake. This here is just an example of a normal fault. So you can see it in action. This here is the fault line. And above the fault line, we have the hanging wall. And below is the footwall. And we can pick a layer like this white one right here, and you can see that this is the same layer. So because the white layer went down on the hanging wall, we know that this is a normal fault, like it says right here. And if we look at along the fault line, you can see this layer is missing it in this part of the section. So this is the relative lengthening. So as you can see, this is a typical extensional environment. The forces are acting away from each other, and there is missing area of this layer. So therefore, that's the relative lengthening. Now, most of the time when you have a extensional environment, you won't only see one normal fault, but you will see a bunch of normal faults, and a lot of the times they are opposing, like will make the so-called graben. Graben is going to be a very characteristic basin, which are bounded by normal faults on both sides. Like this is one side, as you can see, and that's the other side. And they are all normal faults. And this whole structure we call graben. That's another really cool structure where you can see two graben here. That's one of them. And these are also grabens, but they only have the one side bounded by normal faults, and we call those half graben. So graben when you have these opposing normal faults, and half grabens when you only have one normal fault. So that is, and then the areas where you have the uplifting, almost we could say, is what we call horse. So graben, where you got the normal faults, and the along the normal faults, the area drops down. Those are the grabens, and where it goes up or stays up is what we call the horst. This is a pretty amazing explanation for forming mountain and valley systems. And it's very characteristic when you go to Salt Lake City, west of Salt Lake City, a lot of this kind of structure characteristic. That's a beautiful, beautiful graben in Death Valley. As you can see, this here is a fault. And if you look at the fault line, and we pick up a layer. Above the fault line is the hanging wall. I just say hang. And this is the foot wall. And if you pick a layer, let's say this black, white, and then thick black, white underneath, you can see that we have the exact same layer down here on the hanging wall. And this is the missing area, so that's our relative lengthening. And if we look at the other side, there is another fault line right here. So it's a graben, definitely a graben fault. Now, if we look at this side, and we know that this is the hanging wall, because this is above the fault line. Below is the foot wall. And if we pick this layer right here, then you can see that the hanging wall went out, and this is here the missing area. So that's the lengthening. So I hope you do see how all this is working and how it forms and how can we see relative lengthening. And the forces in this case are acting away from each other again. And that's why this area falls. The second important plate tectonic environment is the compressional one. When you have compressional environment, then the most common type of faults are the so-called reverse fault. When we have a reverse fault, here is the fault line. And of course, the fault plane is right here. Above the fault line, we have the hanging wall, as we talked about it. Below is the foot wall. And as you can see, the forces here are acting toward each other. So they are moving together. And if we look at the hanging wall block is moving up. If we look at the certain layers, look what happens here. This is the brown layer. We can see that it moved up on the hanging wall part. And if we look at what happens along the fault line, you can see that this area, in this area, this layer is repeating. So we have it double. This is what we call relative shortening. Relative shortening. So I said that the brown layer repeated is equal with the amount of shortening. This is just a great example of a reverse fault. Here is the fault line. And above the fault line is the hanging wall. Below the fault line is the foot wall. And if we pick a layer, we can pick this white layer right here. It's the exact same as right here. So as you can see, it moved up on the hanging wall. And if we look, this is the area where the layer repeats itself. So that's the relative shortening. There's a special type of compressional environment where the angle of the fault, this is the fault line right here. And as you can see, the angle of the fault is very low, then much less than 45 degrees. So it's less than 45 degrees. In that case, as you can see, the relative shortening, see this is the hanging wall. I just say hang. This is the foot wall. So you can see that the hanging wall moved up. And if you pick out the brown layer on both sides, when the fault line has a very low angle, then you can see that the relative shortening is much bigger than when it's another type, when it's not less than 45 degrees. So this is what we call a thrust fault. In cases of thrust fault, hanging wall can move like hundreds of kilometers over the foot wall. So that's the relative shortening. And this just a really good example of a thrust fault. This here is the thrust fault. And you can see that this block have moved over to the other block here. So thrust fault. This is another really good example for thrust fault. You can see how long the angle is and how long the relative shortening here. The third environment we have to talk about is the transform environment, which happens along transform plate boundaries. And we call these fault lines strike slip faults. And in these cases, the relative motion on the fault has taken place along a horizontal plane, right there. We have two situations. It could be based on the sense of the displacement. If we are standing on this block and looking which way the other one is moving, you can see that it's moving to the left. This is what we call left lateral strike slip fault. Even if we're standing on this side and looking at which way the other one goes, you can see it's still going to the left. You have to imagine yourself being on one side and see which way the other one is moving. So this here is a typical left lateral. On the other hand, if we are using this one right here and we're standing on this block, we looking at which way the other one is going, you can see that it's going to the right. But if we stand on this side, looking at which way this goes, you can see it's still going to the right. So this here is a typical right lateral strike slip fault. Right lateral strike slip fault. Like if you look at the San Andreas fault, the displacement along the San Andreas fault could be as much as 600 kilometers. This is a typical example of a strike slip fault. As you can see, here is the fault line. And if you are standing on this block and you look at which way the other side is moving, you can see that it's going to the left. But if you're standing on here and looking at this way, you can still see that it's going to the left. So this here is a left lateral strike slip fault. So now that we have gone through the different plate tectonic environments and characterized the different kind of faults which are related to those environments, let's talk about the structure of the Earth so we can then start talking about the plate tectonics. The structure of the Earth is also a repeat from physical geology. So since you have taken the class, this is just really a reminder. Remember the three main layers of the Earth is the core right here. This is the inner core, outer core. Remember the outer core is liquid and the inner core and the outer core generates the Earth magnetic field. This pink area is the mantle. And the very tiny layer on top is the crust. So the three main layers, a core, which has the inner outer core. Outer core is liquid. Then we got the mantle and then the crust. Now let's talk about just the crust. The crust is basically where we live, especially in the continental crust. That's where we are right here. We have two kinds of crust. As you can see on this figure, the continental crust. The continental crust is thick, 10 to 70 kilometers, so it's pretty thick. It's buoyant, means less dense than the oceanic crust, and mostly old. Whenever a continental crust forms, it will never be able to do anything. It's just going to stay there. So the oldest continental crust is about 3.5 billion years old. On the other hand, the oceanic crust is very thin. It's right here, this area. It's about 7 kilometers. It's usually much more dense than the oceanic, so it sinks under the continental crust. And it is never older than 200 million years. That's the oldest. So it's relatively young. And when I say 200 million years old, it's the oldest, which is 200. Youngest one is just forming as we speak. If you look up a bigger picture here, you can see that there are some really important parts of the Earth we have to really know. We just talked about the continental and the oceanic crust. And the continental and oceanic crust together with the uppermost mantle will build up the so-called lithosphere. The lithosphere usually is a plate, so lithosphere plate, okay? So the uppermost mantle plus the crust, it doesn't matter if it's oceanic or continental, but the two together is the lithosphere plate. Below the lithosphere plate, we have the so-called asthenosphere. Asthenosphere is part of the mantle, but what is important about it that it's quasi-liquid. What does quasi-liquid means? That it's under pressure, it's capable to flow. So it's capable to flow. This is very important. The asthenosphere is the layer which is responsible for plate tectonics. Underneath the asthenosphere, we have the normal regular mantle. Let's talk about plate tectonics itself finally. I just showed you the lithosphere plate, which is, remember, the uppermost mantle plus the crust. The Earth crust is divided into 12 major of those. These lithosphere plates move in various directions. They move relative to each other. Because of this motion, the plates will actually collide, and they sometimes collide, they pull apart, they slide next to each other. So the three plate tectonic setting we just talked about is happening in real life. Each type of interaction will cause characteristic set of earth structures or tectonic features. We just talked about the normal fault, reverse fault, and so on. The word tectonics refers to the deformation of the crust as the result of the plate interaction. This slide shows you all these major plates. Some plates will have continent on them. Some plates will have continent and ocean. Some plates is just strictly oceanic plate. Like you can see right here, this is the North American plate, and the North American plate will also contain half of the Atlantic Ocean. The other half of the Atlantic Ocean is part of the Eurasian plate, and this is Eurasia as the continental part of this plate. And then the African plate, which also contains half of the southern half of the Atlantic Ocean. So South American plate contains the south part of the Atlantic Ocean. Here is the Caribbean plate, the Cocos. This is really important here, the Wanda Pucca plate, which has interaction with the northwestern part of North America. And here is the Nazca plate, Philippine plate, Australian plate, and so on. You can really see these plates. What makes the plates to move? The older theory, as we know from the history, is that some places in the Earth mantle, we have this so-called hot spot where we have more radioactive elements, which warms up the area, and above that area, the density is smaller, so there is a movement going upwards. And those are the so-called divergent plate boundaries. And wherever it's cooler, because of the coldness, it will be moving down, and that is what we call the convergent plate boundary. So divergent plate boundary, convergent plate boundary. This idea was placed on the fact that when you're boiling water and you have a heat source, right above the heat source is where the water first starts bubbling, because whenever it's hotter, it's less dense, so it's going to move up, and wherever it's colder, it's more dense, so it's moved down. So this is what we call convection currents. But today we know that the situation is much more complicated, and there is gravity involved and other features. So let's look at a movie in which you can see all this new development about plate tectonics.
Current dynamic models have plates moving as part of a gravity-driven convection system that pushes young hot plates away from spreading ridges and pulls old cold plates down into subduction zones. Remember that lithospheric plates, also called tectonic plates, have a layer of crust on top of lithospheric mantle, the outermost rigid part of the mantle. These move as a single unit. The hotter asthenosphere beneath the plates is solid but less rigid mantle rock that can slowly flow. Now let's look at the broader picture. This map shows how the seafloor increases in age with distance away from spreading ridges, such as the East Pacific Rise or the Mid-Atlantic Ridge, where new ocean plate is forming. Spreading ridges stand 2,500 meters higher than deep ocean basins. At a spreading ridge, the ocean depth is only about 3,000 meters. Ocean depth increases with age of the underlying plate, so that where the plate is more than 80 million years old, the overlying ocean increases to 5,500 meters deep. Let's examine the formation of new oceanic plate and how that plate cools with age. As hot mantle rock rises to lower pressure, a small portion of this upwelling asthenosphere melts to form magma that builds the 7-kilometer thick oceanic crust at the edges of two diverging plates along the ridge axis. Beneath the crust at the spreading ridge, there is only a thin layer of lithospheric mantle because it is unusually hot in the upwelling zone. This hot, and therefore lower density mantle rock, supports the 2,500-meter elevation of the spreading ridge. As the plate slowly moves away from the ridge, it cools by conducting heat through the crust to the cold ocean water above. At the same time, the underlying asthenosphere cools and adds to the bottom of the lithospheric plate. Thus, although the crust maintains its thickness during migration away from the ridge, the lithospheric plate thickens and cools to create ocean basins that extend 5 kilometers in depth. A simple way to think about elevation is that the plate is young, hot, and high at the spreading ridge and becomes old, cold, and low during the aging and cooling process. Mathematical modeling of this cooling process illustrates the ocean plate becoming cooler and thicker with age. The temperature at the bottom of the plate is about 1,300 degrees centigrade. Notice that most of the cooling process occurs between age 0 at the ridge and about 80 million years when the ocean plate has grown to about 100 kilometers thick. The upper plate is less than 600 degrees centigrade, thus is the only part of the plate cold and brittle enough to fracture and produce earthquakes. Though still rigid, the lower plate is warmer and can deform in a ductile or plastic fashion. So what force pushes oceanic plates away from spreading ridges? Any mass on a slope is affected by gravity, seen most dramatically with avalanches and landslides. Spreading ridges are broad undersea mountain ranges, and although the flanks of a spreading ridge are a relatively gentle slope, the mass on that slope is humongous. The force of ridge push is 0 at the ridge, but increases quickly with distance and age, pushing the cooling and thickening oceanic plate away from the ridge. Now what about slab pull? We'll consider a 30-million-year-old oceanic plate, which we'll call a slab, subducting at 5 centimeters per year into hotter asthenospheric mantle beneath a continental plate. As the oceanic plate subducts, the warming process takes many millions of years as the slab descends. The deeper part of it is continuously replaced in a conveyor belt fashion by a cooler plate from above. Mathematical modeling again illustrates the temperatures within the subducting oceanic plate. In this example, lithospheric mantle rock in the subducting plate at 150 kilometers depth is 1,000 degrees cooler than the asthenospheric mantle at the same depth. The cooler temperatures mean that the density of rocks in the subducting slab is greater than the density of the hotter asthenosphere. While gravity pulls down on all rocks, it pulls down harder on more dense rocks. This enhanced gravitational force on the cooler and denser rocks in the subducting plate is the slab pull gravity force. Earthquakes, including great megathrust earthquakes, occur on the shallow part of the boundary between the converging plates and within the shallow parts of both plates near that boundary. In addition, there is a zone of rock cooler than 600 degrees Celsius within the subducting plate that remains brittle and within which earthquakes can occur to depths of hundreds of kilometers. Observations of interplate earthquakes and other indications of stress with tectonic plates suggest that the slab pull force is usually larger than the ridge push force. It is noteworthy that fast-moving plates, like the Pacific Plate, generally have a fast spreading ridge pushing on one side while a subduction zone pulls on the other side. In this big picture view, we see that lithospheric plates are part of a planetary scale thermal convection system. The energy source for plate tectonics is Earth's internal heat, while the forces moving the plates are the ridge push and slab pull gravity forces.